Hello everyone and welcome back to this NPTEL lecture series on aquatic geochemistry. This is your 16th lecture and today we are going to start with thermodynamics. In our last lecture, we discussed about the sources that controls the water composition of rain, of rivers, lakes and oceans. In this lecture, we are going to understand little more about about the compositions. Okay. So, let us right away dive in. Okay. So, whenever we are trying to understand the compositions, we have to start with the basic fundamental tools that we have in physics and chemistry, and that is thermodynamics and kinetics. Okay. Now, thermodynamics is the most fundamental tool of geochemistry, and most other when we are trying to do speciation modeling, when we are trying to understand which mineral is going to get weathered and the reactions, we are going to write the reactions which is going to give out calcium, sodium, whatever we are writing the transformation reactions, that is one particular mineral is getting weathered and getting transferred to another type of mineral, and during that process of the transformation there are elements that are getting exchanged. Okay. So, this kind of understanding the basic weathering reactions requires a lot of understanding of the thermodynamics and the kinetics of the system. So, thermodynamics allows us to predict and calculate the composition of the natural waters. So, from the bedrocks, okay, so we are having first thing what we will have an understanding of the bedrock, whether it is exposed. Okay. So, there is the watershed, whatever kinds of rocks are there, okay, we will study, okay, this kind of rocks are there. Okay. Now, among all these rock types, there will be some rocks which will be more weathered, there will be some rocks which will be less weathered, and even in the rock types there will be certain minerals, okay, which will be more undergoing more weathering reactions as compared to other minerals which are more of the hard type, and they will take a lot of time to interact. Okay. So, every system, to understand what kinds of reactions are going on, first we will try to understand whether it is whether it is a equilibrium reaction, whether it is a non-equilibrium reaction, which direction is the reaction proceeding. Okay. All that kind of understanding thermodynamics will give us. Okay. How much reactants are there, how much products are there, which side is the reaction moving, such kind of understanding only thermodynamics will give us. Okay. So, the very the very basic understanding, okay, that which minerals are going to dissolved, okay, when are they going to get precipitated, okay, which new minerals will start forming, in which phase they will be, okay, how will one particular chemical species alter the solubility of another species, okay, what will be the interaction with other kinds of phases. For example, there will be nutrients, there can be organic matter, there can be organic carbon, there can be a variety of other type of contaminants can be there. Okay. Chemicals, by contaminants I mean new type of chemicals that are introduced by humans into the system. So, how their interaction and their reactions will be. So, now when I say all these reactions, so whether certain complexes are going to get formed, certain new minerals are going to form, okay, what is precipitating, what is dissolving, all this understanding thermodynamics will only give us. Okay. So, thermodynamics gives us the most basic framework of understanding the chemical processes, okay, and therefore, what reactions are happening in soils, rivers, lakes, oceans, groundwater, with the sediment interactions, at the hydrothermal vents, anywhere where there is mining and there is mineral interactions are going on. Okay. And even not only on earth, but in other planets also. Okay. So, for example, water related science and the search for water, the search for products which are related to water is continuously going on in all the space related missions, okay, where they can find water, where they can find other products which would hint that okay, this is related to water, something has happened either in the past or due to temperature changes it is not there. So, something related to water they will get a signature. Okay. So, all the space missions they are continuously searching for that. Thermodynamics is important. So, to give us a boundary basically that okay, this can happen and this does not fulfill the conditions for this particular reaction to happen. Okay. So, it gives us that kind of framework, it gives us that kind of boundary to work with, but it also has its own limitations. Now, what are the important limitations? Okay. It is only useful in understanding equilibrium situations. Okay. So, when you are having equilibrium condition, then you know okay, that okay, this is definitely a reaction that is. So, now understanding this equilibrium situation is only sometimes a little difficult, whether it has reached its equilibrium state, whether it is not reached equilibrium state, whether there are what changes are there, okay, that is continuously changing, right. So, in natural surface water system equilibrium is always changing. Okay. So, that is the reason sometimes thermodynamics can get limited, and the fact that Earth's surface temperature is very low such that equilibrium is never reached. Okay. Equilibrium, to reach equilibrium one has to increase the temperature, okay, because when the temperature increases the equilibrium potential also increases. Okay. So, due to that the thermodynamics is mostly useful at the temperature that is having very high temperature. So, mostly in hydrothermal vent interactions or due to any type of interaction where there is a lot of heat available, okay, heat energy is available. So, therefore, equilibrium will be reached in those cases. At temperatures relevant to the earth's surface, most geochemical systems they will not be in equilibrium, okay, and therefore, there will be continuous reaction going on, and that reaction is mostly driven by kinetics. Okay. So, thermodynamics and kinetics we both need them understanding both the thermodynamic aspect as well as the kinetic aspect to understand our reactions. Okay. So, only thermodynamics will not give you a lot of information, you will also need to understand the kinetics of it, because most situations on the earth's surface, most systems on the earth's surface they are not in the state of equilibrium. So, therefore, their reactions, their interactions, okay, those aquatic systems they are mostly driven due to kinetics. Okay. Now, reactions are not instantaneous. Okay. So, therefore, minerals they will take some time to dissolve, these minerals will take some time to precipitate. Okay. Now, kinetics which gives us a time sense, okay, they are therefore important. Okay. Whether the complex will form, whether it will dissociate, what at what rate ion exchange is going to happen, all this wherever there is a reaction going on, at time becomes a very important factor for certain reactions, okay, which is the most rate limiting reaction, understanding which is the most rate limiting reaction, that becomes very important. Okay. So, therefore, kinetics becomes our very important topic. So, we are going to among all the processes that we deal with, we will have thermodynamics and kinetics are very important. And in certain modeling, hydrogeochemical modeling techniques, and in understanding speciation and all that, thermodynamic and kinetic information is extremely important. It is all the databases that they have and all the models, ready-made models, if you see, they will already have a background. Okay, they are built on these thermokinetic models. Okay. So, if you want to develop more on those areas, you need to have a deeper understanding of thermodynamics and kinetics of the system. Okay. But otherwise, more or less the work has been done, and now you just need to add those variables. You will need to add the temperature, pressure, what other chemical constituents are there, and you can easily derive what kind of situation, what kind of equilibrium situation, kinetic reactions going on, what should happen to this mineral, what should happen to the whatever is precipitating out. So, a lot of experiments has already happened, and we already have generated a very significant amount of understanding, okay, in the field of thermodynamics and kinetics. Now, other than thermodynamics and kinetics, there is a lot of other continuous processes that is happening, that is changing the natural water composition. So, it is not only the weathering, but also a lot of other continuous processes. For example, okay, we mentioned temperature, we mentioned pH, dissolved oxygen, salinity and TDS as important parameters that we should monitor for our water quality parameters. Okay. Now, why are we measuring pH, right? Why are we going to what information will pH give us? pH will give us that information that whether that system will have any acid and basic reactions or not, right. What kind of reactions are happening? Is it of the acid and base nature? That is extremely important. See, reactions, equilibrium in nature, not equilibrium in nature, that is a different thing, but their types, okay, they are dependent on these physiochemical parameters, right. So, another very important controller is dissolved oxygen. Dissolved oxygen, all those elements which are whose solubility varies with the redox states, which exist in different redox oxidation states, their solubility, their mobility sometimes are dependent on those particular oxidation state. For example, uranium, for example, iron, manganese, they are having different redox states, right. Sometimes they will precipitate under oxidizing conditions, sometimes they will be remain mobile. For example, uranium, okay, uranium there are two redox states, one is uranium 6 and one is uranium 4. Okay. Uranium 6 is the more mobile, more soluble kind of component. Okay. So, under oxidizing conditions, okay, whenever there is oxidizing conditions, that time uranium will be in its higher redox condition, uranium 6, and it will become more soluble, it will become more mobile during this more oxygenated state. Similarly, iron, okay, iron is also a very redox sensitive element. Okay. It exists in two states, Fe2 plus and Fe3 plus. Now, Fe2 plus is the more soluble, it is the one that is in the dissolved state. As soon as it is oxidized, that is it is in the Fe3 plus state, then it gets precipitated out. Okay. So, under oxidizing conditions you will see iron will precipitate out and it will settle down as iron oxide, okay, either iron oxide or hydroxides. So, in different kinds, so basically iron will start precipitating out. So, due to this redox shifts, a lot of compositions can get changed. There is redox related mobilization that can happen at different locations, and in the same river, if you are monitoring a river from its two particular points, okay, say you have a point A and you have a point B, okay, and if you are monitoring that river in between these two locations, okay, then you will see that their chemistry is not exactly same. There will be certain differences in the major ion composition and also in the trace elemental composition. Okay. So, there is because of this continuous interaction, okay, that is because of this continuous interaction. Okay. Then salinity, okay, again an extremely important parameter. What it happens? It can cause adsorption, desorption related changes, okay, and each kind of reaction we are going to look into details in our future lectures. Okay. Solubility and aqueous complex species, all the organic composition. So, the total dissolved solids whatever is there, that controls the solubility and the aqueous complex formation in the water. Okay. So, these continuous interactions causes changes in the chemical composition, and therefore, you see in different locations the composition will be different even for the same river, okay, that is flowing through the same lithology, okay, that is flowing through the same bedrock area also, there will be certain compositional changes. It all depends on these reactions and at what rate they are happening, okay, at what rate. So, therefore, the thermodynamics, okay, and the kinetics both are important to note down. Other than that, chemical weathering, okay. So, chemical weathering of silicate rocks and carbonate rocks. So, that again, so they are the most important fundamental, again I will repeat this, they are the most dominant source of solutes in any aquatic system. Okay. So, they form the first hand solute composition which continuously gets evolved. And then organic and biotic interactions, okay. They are again of very variable nature. It is extremely difficult to predict based on a particular system. They are continuously evolving, they are continuously changing with this with the season, with temperature, with dissolved oxygen. So, their interactions are extremely variable, okay, and often this is not considered a lot of times. If you see studies which are mostly focusing on weathering, you will not see a lot of organic and biotic interactions being considered, and that is because they are both of plus, and that is they are also releasing and they are also uptaking. Okay. So, whenever there is a uptaking, the concentration in the water is going down, and whenever they are releasing into the system, okay, the concentration is increasing in that aquatic system. But this is continuously happening, right. So, they say that it is expected that this is in equilibrium. So, the release and the uptake, okay, they are in equilibrium, therefore, there should be no direct changes in the aquatic system. But it can always if you are trying to understand much better way the organic interactions, then you do need to look into organic and biotic interactions. Okay. Now, what type of questions are we looking in chemical thermodynamics? Okay, what do we look in, what do we do with thermodynamics? Okay, how do we apply thermodynamic concepts in aquatic geochemistry? Okay, in this particular lecture series, I am not going to discuss a lot about thermodynamics. I am just going to bring out that aspect of thermodynamics which is most relevant to understand the aquatic composition. Okay. So, no point of time you need to memorize the reactions, or you need to memorize any values or anything. Okay. What is important is that you understand how the reactions are written down, how to calculate the equilibrium constants, how to say whether a reaction is going to happen or not. Okay. So, those are the important things that I expect you to learn from this the scope of this lecture series. Okay. So, when we look into equilibrium calculations, there are two questions that we are going to ask. First, whether in a system we are reaching a chemical equilibrium, whether the system is at chemical equilibrium or not, and what reactions are therefore occurring. Okay. If it is not in equilibrium, what likely reactions are happening. Okay. So, let me give you a certain example of this kind of situation. As an environmental geochemist, very often we come in different kind of situations where we have to provide solution. Okay. And mining, okay, causes a lot of pollution and a lot of degradation to aquatic systems. So, if you are an environmental geochemist, your role will be to understand the system better, develop the understanding of not only the current state, but also what it can look like in the future, and therefore provide certain solutions. So, in that regard, suppose you are taking consider there is a stream, okay, that got contaminated by waste material due to silver mining going on. Okay. And after mining, what happens is there is a time where the mine is closed and is left just to recover, that is the recovery stage. Okay. And for example, this mine which they have completely finished their mining work, and now only the waste products are remaining there in the system, that is left to recover for it is generally left for a very long time. So, that natural activities like soil formation and or growth of plants and all that, they only take over the entire system, and the system starts getting restored. Okay. So, that kind of system you are looking at, and this has mine which has been abandoned for almost 10 years. Okay. Now, this particular stream, okay, which got contaminated due to this silver mining activity, discharges into an estuary. What is an estuary? Estuary is when a river is meeting the ocean, and if there is a lot of sediments that is coming in, the river mouth is not that spread out such that it forms a large delta. So, it forms like a small estuary system. Okay. So, there can be either an estuary or a delta. And this particular stream is discharging into an estuary. Okay. So, it is very close to the basically it is mixing with the ocean. So, what is happening, all the contaminated water is getting released in the ocean, and silver is not a essential element, it is not an essential element for the body, it will act as a toxic contaminant, and if the contamination level is very high, then the threat can come for the marine ecological system. Now, whenever there is mining activity going on, it is not only the particular mineral that you are mining or the particular element that is getting mined, all the other elements that is released from that mining is also very important. For example, silver mining generally happens from this ore called argentite. Okay. So, this argentite is basically a type of sulphide rock. Okay, it's a ore is basically of sulphide nature. Now, all the other elements which are sulphide loving, okay, they will also be found in higher concentration in these types of rocks. So, you will find a lot of copper, you will find a lot of arsenic, all these elements associated with sulphide rocks. Okay. Now, since all these rocks have been exposed, arsenic and copper, it is very easy to leach them from these rocks to the stream and therefore to the estuary. As you all know that arsenic is a type of toxic element. It can have a lot of health effects on different types of organisms. Okay. And even in humans, arsenic is very important, it causes a lot of health effect. It is a very key element that we see in water quality, and you will see arsenic being monitored because it has a lot of diseases, especially skin diseases, and sometimes very chronic illness can occur due to arsenic. And copper, although it is an essential micronutrient, but beyond a certain concentration it can also start becoming toxic. So, copper and arsenic, they can get released to the estuary, and through the mixing of the waters it can get spread out into the ocean. So, your questions will be that you need to answer are: what fluxes of elements such as copper, arsenic are going to the estuary? What is the form of that particular pollutant in different phases, in the dissolved phase, in the sediment phase? Okay. Is it is continuously dissolving? Is that a reaction still happening? Okay. Also, is there any other, is the presence of copper and arsenic or silver, is it changing any other particular chemical, okay, that is already there in the environment, from being harmless to becoming deadly one? Okay. Or if something is moving from the deadly state to the harmless stage. Okay. So, what kind of reactions is happening? Okay, we need to understand that. Okay. Now, all these kind of questions we can make simple equilibrium calculations. Okay. For example, the first thing that you are going to find out is that arsenic has two main oxidation states, and that is in the 5+ states and the 3+ state. Now, which oxidation state is arsenic is? Okay, because one particular state is soluble and therefore mobile, and the other is not so soluble, not so mobile, and therefore not so toxic. And we are going to be worried about only that state which is more toxic in nature and more mobile in nature. Okay. So, arsenic 3 or arsenite is the more mobile and toxic as compared to this arsenic 5 stage. Okay. And this reaction can be written as follows. As you can see, H2SO4 minus, if it reacts with hydrogen and exchange electrons, it is going to form this compound. Okay. Then we are going to calculate which is the most stable form in the oxygenated surface sediments. Okay. Oxygenated surface sediments means whether there is any kind of anoxic region within the sediments. Okay. So, suppose the stream is there. Okay. In that stream, if the sediment layer, okay, if the top sediment layer, if that is oxygenated or not. okay, if there are anoxic reactions happening absolutely at the bottom or not, or if the entire sediment of the stream is in what state, whether it is in the oxic state or whether it is in the anoxic state. We need to find out that. And then we have to find out, okay, if it is an organic rich sediment, okay, if there is high organic rich sediment, where is that reduction happening, where there is sulphate reduction happening such that it can release, okay, copper and arsenic back into the system. Okay. So, we need to understand the occurrence of these reactions. Okay. So, we need to find out certain things from the field sites, okay, and we need to make certain reactions, and we have to make ourselves to be able to answer those questions, that is which according to this okay. So, we find out it is a oxic environment. Now, if it is oxic environment, which arsenic, which form of arsenic is available, that we need to calculate based on the chemical equilibrium situation. We have to find out which oxidation state of arsenic is present. Okay. Then we can find out, okay, if there is some organic compounds are there or not. If there is organic compounds are there, can we see any sulphate reduction happening? Can we see that particular reduced oxides and all that? Okay. If yes, okay, now let us look into the reactions, let us make certain reactions. So, that is how we proceed using our thermodynamic understanding. Today we will stop here, and in our next lecture I will continue to give more examples and we will move on to details.